Hey everyone, Mr. Hauk here. In today's video, we're going to be proving the Pythagorean identities. Let's go ahead and get started. So the purpose of today's lesson is to go ahead and use the Pythagorean theorem to prove the following Pythagorean identities, which are right here. And what we're going to be able to do with this, once we have these proven, is we're going to be able to use them to help us simplify a lot of trigonometric expressions. So to start this, let's go ahead and think of the first quadrant of the unit circle. And when we were studying the unit circle in the first semester, we were making a lot of right triangles. Where notice that for the right triangles that we would make in the unit circle, the hypotenuse is the radius of the triangle. And since it's the unit circle, the hypotenuse is going to be 1 because the radius of the unit circle is always going to be 1. So this creates a right triangle. And we studied a lot of these right triangles in first semester. We know that when we're talking about an angle theta down here in this corner, well, if we were to take the sine of angle theta, it'd be the opposite side divided by the hypotenuse. Well, whatever this opposite side is, whatever this sine is, because it's being divided by 1, sine divided by 1 is still sine of that angle. So this sine of theta represents this entire side. Cosine of theta represents this entire side. So this is the x value, this is the y value, and that's why when we were looking at the unit circle, when we look at points, like for example that point on the unit circle, this was cosine theta, sine theta. That's why we're saying, the x value is cosine, the y value is sine. That's because on the unit circle, the hypotenuse is 1, okay? But now let's think about it more in terms of right triangles. So we know that Pythagorean's theorem, a squared plus b squared equals c squared, that only works for right triangles, but those are the kinds of triangles we're working with on the unit circle. So let's go ahead and let this be a, cosine of theta be b, and of course the hypotenuse, 1, is going to be c. And let's go ahead and prove these three results, which is also going to allow us to have some variants of these Pythagorean identities. Okay, so let's start with the first one. Let's prove that sine squared of theta plus cosine squared of theta equals 1. So let's see here. Again, we've already said that a is going to be sine of theta. So let's go ahead and write some information down here. A equals sine of theta. B equals cosine of theta. And C equals 1. Then, by Pythagorean's theorem, we have a squared plus b squared equals c squared. Well, let's replace a, b, and c with sine theta, cosine theta, and 1. So a squared would turn into sine of theta squared. B squared would be cosine of theta squared. And c squared would just be 1 squared. But in mathematics, sine of theta squared, we write it like this. Sine squared of theta. And cosine of theta squared, we write as cosine squared of theta. And 1 squared is, of course, 1, but that's exactly what we wanted to prove. So this identity, it's called the Pythagorean, these are called the Pythagorean identities because they are the direct result of Pythagorean's theorem with a right triangle in the unit circle. Okay, so let's go ahead and put our little rectangle show into proof. We finished our proof. That's the exact result that we wanted to show. Now, once we have this result, though, the sine squared of theta plus cosine squared of theta equals 1, we can then get some variance. Notice that if I took this formula and I subtracted sine squared from both sides, like this, on the left, of course, it would cancel out, and we'd be left with cosine squared of theta equals 1 minus sine squared of theta. So that's one of the variants of this version of this Pythagorean identity. We could do the same thing. If we wanted to isolate for sine squared, we could subtract cosine squared of theta from both sides. That would cancel here, and we'd have sine squared of theta equals 1 minus cosine squared of theta, which is this variant right here. So these three, all the same statement, they're just rearranged versions of each other. Okay, so there's our first one that we proved. Let's prove the next one. Now let's prove that 1 plus tangent squared of theta equals secant squared of theta. And what we're going to take note of, well, let's go ahead and take what we've already proven and let's just mess around with it. So we already showed that sine squared of theta plus cosine squared of theta equals 1. So let's take that result and now let's use it. So sine squared of theta plus cosine squared of theta equals 1. And let's see. Let's try this. Let's try to divide both sides, all terms on both sides, by cosine squared of theta. You might wonder, well, why on earth would you divide everything by cosine squared of theta? That seems so random, right? Well, it's actually not really random. Think of secant squared. We know that secant squared is the reciprocal of cosine squared, or secant is the reciprocal of cosine, so secant squared would be the reciprocal of cosine squared. And I already knew I had this 1 over here, so if I could divide it by cosine squared, that would give me the secant squared. But if I divide this side by cosine squared, I have to divide everything on this side also by cosine squared. So that's kind of the thought process there. So let's go ahead and simplify and see what happens. So sine squared of theta divided by cosine squared of theta. Well, we know sine over cosine is tangent. These are both being squared. So sine squared of theta over cosine squared of theta is tangent squared of theta. Cosine squared of theta over cosine squared of theta cancel to give you 1. So this is plus 1 equals, and of course, just like we were mentioning a moment ago, 1 over cosine is secant. So 1 over cosine squared is going to be secant squared of theta. And that's exactly what we wanted to prove. Notice in my version here, I have the tangent squared of theta, then plus 1, but we know addition is commutative, so we could add these in any order. It's still the same statement. And that's exactly what we wanted to prove. Now, just like the previous identity, we can rearrange this to get some variance. Notice that I can take, for example, this plus 1. I can subtract it from both sides, and I get this statement right here. Tangent squared of theta equals secant squared of theta minus 1. Or I could take the tangent squared and subtract it from both sides. That gives me this statement right here. 1 equals secant squared of theta minus tangent squared of theta. So there's our variants that are really just rearranged versions of this equation, okay? Now let's prove our last Pythagorean identity. And once again, I'm going to kind of start it the same way. We already showed sine squared of theta plus cosine squared of theta equals 1. Now, let's think about this, and we're going to use a very similar technique. We want the right side to be a cosecant squared. Well, we're only going to get a cosecant if we do 1 divided by sine. So if I do 1 divided by sine squared, I'll get a cosecant squared. So let's divide everything by sine squared of theta. Okay, again, we have to divide everything by the same term because we need to maintain the balance of the equation. So let's see what happens here. All right, well, sine squared over sine squared, that's going to cancel to give you 1. We know that cosine over sine is another way to write cotangent. So cosine squared theta over sine squared theta is going to be cotangent squared theta. And we know that 1 over sine is cosecant, so 1 over sine squared of theta is going to be cosecant squared theta, which is the exact result that we wanted to prove. Oh, wanted a laser pointer. There we go, right there. That's the exact result we wanted to prove. Let's put our little into proof rectangle. And then once again, real quick, notice that if we rearrange this equation, we can get these variants right over here. First one by subtracting 1 from both sides. Got that right there. And we can also subtract the cotangent squared from both sides. And that'd give you this variant right there, okay? So short video today, just proving the Pythagorean identities, and then we're going to start using these identities and all the different formulas and identities that we've derived to start simplifying trig expressions. That'll be in the next video.